Welcome to Zibran's Curiosity Universe. Let's discover why time slows near a black hole. Two perfect clocks leave together. One stays far from a black hole. The other travels closer, still safely outside. When they meet again, will they show the same time?
My guess is no. But how can gravity change time?
Curiosity mission accepted. Find the spacetime key before both clocks reunite.
This is a thought experiment. Our ship remains far outside the event horizon, and nobody is in danger.
Prediction time. Which clock will show less elapsed time, the farther clock or the closer clock?
Choose now. Farther or closer? I choose closer.
Einstein's relativity tells us that space and time are joined as spacetime. Mass and energy curve spacetime, and clocks following different paths can accumulate different amounts of time.
So gravity is not reaching inside and breaking the clock?
Correct. Each clock works normally where it is. We notice the difference only when we compare them.
The effect happens on Earth too. A clock slightly lower in Earth's gravity runs a tiny bit slower than a clock higher up when scientists compare them.
NIST atomic clocks can measure differences this small. You would not feel it during breakfast, but precise clocks can detect it.
Then a black hole is the giant version of a real effect.
Exactly. Near a black hole, gravity is far stronger, so the clock rate difference can become much larger.
Watch the two labeled clocks. The farther clock advances normally. The closer clock also feels normal beside the ship, but compared with the farther clock, it accumulates less time.
The clock hands are not stuck. Their journeys through space-time are different.
Imagine Zibran sends one light signal every second. To Zibran, every signal leaves on time.
A faraway observer receives those signals increasingly spread out and shifted toward red. The nearby clock therefore looks slower from far away.
But on my ship, my heartbeat, thoughts, and clock all feel normal.
Both descriptions can be true because the observers follow different paths and compare time using exchanged signals.
Does 1 year near a black hole always equal 10 years far away?
No. There is no universal 1 to 10 rule. The difference depends on the black hole, your distance, your motion, and exactly which clocks you compare.
Movies may choose a dramatic ratio. Science must state the conditions before using any number.
Reunion quiz. Clock F stayed farther away. Clock C traveled closer and returned. Which clock shows less elapsed time?
Think for 3, 2, 1.
Clock C, the closer clock, shows less elapsed time. That is gravitational time dilation.
Less time on the returning clock does not mean time vanished. It means the two clocks measured different durations along different journeys. Relativity is not only a black hole idea. GPS satellite clocks experience effects from both gravity and motion.
Engineers correct those differences so navigation stays accurate. Without relativity, precise positioning would drift.
A question about black holes helps explain the map on a phone. That is a brilliant connection.
Curiosity boost for older explorers. Scientists call the time measured along one traveler's path proper time. Different paths through curved spacetime can have different proper times.
You do not need the equation today. Remember the comparison, same departure, different journeys, different elapsed times.
And what is the glowing boundary around the black hole?
That clue belongs to our next mission. It is the event horizon, a boundary beyond which light cannot escape to the far outside.
We remain safely outside it. Episode 2 will ask what an event horizon really is and why it is not a solid wall.
Spacetime key unlocked.
My 3 discoveries. Stronger gravity changes clock comparisons. My own clock still feels normal, and the amount is not one fixed ratio.
Now make your prediction. If two identical clocks reunite after different gravitational journeys, what should scientists compare?
their elapsed time, and the paths they took. Keep wondering. The Event Horizon mission is next.
Mission quiz. If light from beyond the event horizon cannot return, how can scientists study a black hole? A. Measure its gravity and the light around it. B. Send a camera inside and bring it back out. Or C. Touch the event horizon like a solid wall. Keep your answer. We will reveal and explain it at the end of episode 2.
Great thinking. If you liked this adventure, watch the next mission and subscribe to Zibran's channel.